Great, thank you all for having me. So let's get started. As Regina mentioned, I'm going to talk about how do we actually build these better risk models, starting from the innovations that brought us to our published results back in May, and also all the things we've done to make it much better, ways to improve both accuracy and calibration. And then kind of close the gap to impact. If you have a better risk model, how do you actually use them to change care, to do something better about it? And it turns out machine learning can do a lot of help there. I'm going to close the call to action and how we need your all's help to help us to actually bring this to impact. So let's get started. As Regina said, and as you can guess by now, I'm going to talk a lot about predicting future cancer risk. Which of these two breasts is actually going to result in cancer within the next 5 years? And for the initial results, I'm going to kind of delve into more detail for the paper. The kind of base is really just a standard architecture with special tricks to make it stable and actually fit the task. I'm not going to go into details that are written in the paper. But the kind of first two models we looked at is one is just a deep learning model based on the image by itself with no auxiliary information. You just take this standard view, CCMLO, you train a deep neural network to kind of learn cancer in 5 years or not, as a kind of a binary task, yes, no. And the other, which Regina alluded to, where you're also allowed to look at the same risk factors as the hierarchic model. And the initial results we found, all this is 5-year risks, and so the kind of numbers are shifted accordingly, is that even the image by itself, with no other information, no age, nothing else, can only be the hierarchic model, AUC 68 compared to 62. And by adding these additional risk factors, we can get another small bump in performance. And something else we saw is that this gap in performance wasn't just across the whole population, which is this kind of test set of about 4,000 patients, but also across different subgroups. So you see here on the left-hand side we have performance on white women, whereas the performance is fairly similar. But in African-American women, we see the model's performance hold, and whereas it drops worse than random for the hierarchic model. Moreover, for every different subgroup we looked at, whether be it pre-menopausal, post-menopausal, with family history, without family history, in every way we could slice the data, we found the same trend. So, but this is the kind of brings us up to date with the results we published back in May, but obviously we didn't stop working then. There's lots of new technical innovations you can do to make the model better. One of the first flaws that we had in our original formulation was the way we very much thought about risk in the first place. The risk isn't a binary task. It's not you get cancer in 5 years or not. There's a difference between near-term risk, i.e. cancer in 3 years or 1 year, versus 5 years away. And so we thought, how do we change our modeling formulation to take this into account and learn a better model accordingly? Now, some of you might be familiar with things like the Cox proportional hazards models. It makes this assumption that maybe our features really don't have to do with the time dependency, and you can kind of estimate just the relative hazard. But in breast cancer, we know this isn't true. What I mean by this is that the features that mean no cancer today, i.e. no visible tumor or anything of that sort, is not the same thing as the features that mean no cancer in 5 years. So we need to change our modeling to learn the way the cancer represents over different points in time. And so to do this, we came up with something called the discrete time survival formulation, in which we start with the notion that, what is a 5-year risk really? Well, it's a baseline risk, and then the risk in that next year, and then in that next year, and then the next year accordingly. So then we design a neural network layer to take this idea into account and specifically predict this kind of baseline risk idea and the additional risk over time. And then we can then optimize this new objective across observational data at scale. This lets us not only use much more data than before, but also give you coherent risk curves of how does someone's risk change over time across the near future. Beyond that, we also realized that the traditional risk factors, as we used them before, are a giant pain. People here know better than I do. Collecting them can be both a very erroneous and expensive process. And as we learned to both try to solve these inside MGH, but kind of share results more broadly, they offer a major hurdle. So one of the ways we found to kind of step beside this is that we can actually use these risk factors at training time to make the model better and remove the dependency at test time. And the way we do this is via something called multitask learning. So what we do is we start with a base model looking at the image, and we ask it to predict the identity of all of these risk factors from the image. So how old is the woman? Is she pre or postmenopausal? What are all these other questionnaire factors from the image itself? And if the risk factor information isn't available, use those predictions to feed back into the model. We found by doing this, when we remove the risk factors, we actually get no performance degradation, but we can also make the model itself stronger by offering kind of additional kinds of auxiliary signal. And lastly, we also changed the way we look at the different images at the same time. And the original paper looked at one image at a time and kind of tried to learn this independent relationship. But now, through kind of more technical innovations, we found ways to jointly model how different views come together to give you a more powerful signal. So these are all ways to kind of drive the actual performance and accuracy of the model up. But this isn't the only challenge in risk modeling. As many people know, there's also this notion of how well calibrated is the model. Does the number you're saying mean the same thing for every patient? And to do this, we ran into some finicky issues in which we found that if you just run the same model on different machines at MGH, which are both different generations of whole logic, what a 5% risk meant would change. What that means is that for different devices, even though it would stay accurate within a device and could accurately separate away high risk from low risk, all the numbers would change. This is one of the many ways in which kind of small biases in data collection can represent themselves. And so to deal with this problem, we use something called a conditional adversarial training setup, in which we train the model to specifically throw away this kind of device irrelevant information and only rely on the information that's really relevant for predicting risk. And the way that this works is as follows. Instead of viewing our model as one big monolith, we're actually going to predict into 3 players. There's going to be an encoder that's going to say what part of this mammogram is relevant, a predictor that uses that information to predict risk, and a discriminator whose job is to catch things we don't like, as in which device did it come from, or possibly in future work, other kinds of biases we're trying to resist against. And by training these players to work against each other, by having the encoder and the predictor try to do the best they can to predict risk while fooling the adversary, and training the adversary to do the best job it can, we can actually remove all of this confounding information. And so this kind of builds up to this picture that Regina showed you earlier, and lets us have a much more powerful model. So this kind of builds up to these results here. This measure is called C-index, which is a generalization over AUC over time. And what we find is that whereas our kind of prior state-of-the-art was Ty-Cusick was 63, our prior models got to 73, and now through these kind of different modifications, we have a score of 78. We're moving this model over to Karolinska with using 0 risk factor information. So this is only the image by itself. We saw our performance didn't degrade at all and actually was slightly higher. So this has all been about so far, how to actually build these better risk models, but why does that matter? Without a way to use these risk models, these are just numbers on a page, and what we're really driving for here is doing earlier detection and driving impact. And I'm going to argue that our current guidelines by themselves, things like 20% lifetime risk or 1.67 5-year risk, aren't good enough to truly drive that impact. So let's kind of think about this problem more seriously. If we're going to think about how do we catch cancers earlier, it's 2 problems. One, better risk, but also better ways to use it. And what we intuitively, we already do some kind of risk screening, as in we have ages where mammography is available for people, because age is itself a weak risk marker. But given we have something more powerful than just age, i.e. risk models, we should be able to understand who should be screened sooner, who can afford to get screened more late, to get better early detection, while still balancing against the cost of image costs and screening harms associated. So the first challenge in figuring out how do you build personalized screening models is how do you evaluate them. And the first insight I'm going to talk about is you can actually use longitudinal screening data as a model itself to simulate different possible guidelines. So we're going to look at all the different longitudinal trajectories in the test set that we have already at MGH. And we're going to look at these kind of trajectories and measure a couple metrics. The first of which is compared to the actual amount of images that happened, how many more images did you recommend? Obviously, if you tell everybody to get imaging every day, you will have maximal chance of early detection, but there's a lot of harms associated. So this is a metric we're going to call image utilization. Another metric is how many diagnoses would you have delayed by telling someone to come back later than they should have? Or a corresponding metric for people that had a kind of interval cancer, how many people did you tell to come back in that interval before they were diagnosed? So these are possible metrics that you can use to kind of evaluate your screening policy, and you can look at any policy, learned or not, under this framework. How does annual screening do? How does biannual? How does the other nations' screening programs do when we look at them head to head? But another thing it lets us do is now we have this kind of simulation environment, we can actually learn this as a reinforcement learning problem. What that means we can train an AI to look at your risk profile, predict who should come back in 6 months or a year, should you get MRI or not, and specifically optimize in this model the trade-off between earlier detection and imaging cost. And so this is exactly what we did here. We're going to compare to kind of these kind of standard guidelines. What we found is that we can use less imaging overall than annual screening on average, have better earlier detection without harm. Now, what this means, though, is really all about the trade-off you're choosing between how do you balance your imaging cost versus diagnosis cost. So some very reasonable questions are like, are these even the right metrics? Maybe the right metric is QALYs. Maybe the right metric is, are we benefiting the younger women the most, or people with the most aggressive forms of cancer? There's many possible metrics to think about. And also, who should choose this trade-off? I will argue, not me, as a computer scientist. But really, this is a kind of a clinical question, a question for healthcare systems about what do they want their screening program to do, both in terms of inside hospital systems and across nations. And so the solution we're proposing here is not a one-size-fits-all approach, but one that supports a wide library of possible metrics. And if you have ideas of other metrics you'd want, please contact me because I'm willing to support them. But also a learning setup that lets you choose how do you rank the trade-off yourself and automatically get an optimal policy to optimize for that. This idea in the technical sense is something called multi-objective RL, where we train to support the whole diverse plethora range of different preferences and how you weigh these trade-offs at the same time. So as the user and as the health system, all you say is, here is my screening objective. I want this much early diagnosis and this much imaging cost, and I want this much of it to go to the most aggressive forms of cancers, and automatically generate policies accordingly. And with that, we'll be able to beat age-based screening regardless of the objective. Now, a reasonable question then is what's next? Hopefully by now I've convinced you we have some tools and that are promising so far, but for us, we really want to make sure this works, and our ultimate goal is changing the way we think about guidelines today. And we want to do this to serve cancer patients globally. So to this end, we've worked very hard so far to start conversations and collaborations with hospitals across the world, and this is where we need your help. So sometime midsummer, we applied to ACRIN for the trial data to see, are we actually serving all the populations that we need to serve? This is actually work for every single patient. But also, we're working to set up any individual site-to-site collaboration for people interested in both using these tools and also joining us in this mission to make sure that they serve the entire population. Now, with that, I'd just like to thank you. Obviously, this work will not be possible without the lab and the fluffiest dog, which is my dog, and my fantastic collaborators at MGH and MIT. Thank you all so much.